Okay, so in this video, we are going to review all of Chapter 8. So we finished covering Chapter 8, but there's a lot of material. So we've sort of done one example of in a few different ways in class, and now I want to take another few examples and do another example and do that a few different ways. So just to remind you, this notation ends up being sort of important for this chapter, so I just wanted to remind you what it means, the Z alpha notation. So alpha here is something that corresponds to the confidence interval. So if I were to say that an alpha is 0.05, that number, that alpha is 0.05 means that I want 95% confidence. Same if alpha was 0.1, that would be that I want 90% confidence. So this language is pretty prominent in statistics. So it's good to be comfortable with what alpha means. And where alpha comes into play is that alpha is this number here, which tells you the area to the right of the curve. So for a Z value of 0.76, the area to the left of the curve, which is what you would get when you look this up in a Z table, would be 0.7764, which means that the area to the right of the curve is 0.2236, 22.36%. So Z of 0.2236 is 0.76. A more common Z value is this one right here. It's the Z value that corresponds to our 95% confidence intervals. Because when we are looking for 95% confidence intervals, we want to find the area such that this right here is 2.5% of the area under the curve. But there's a matching one over here that is also 2.5% of the curve. So if we're looking for a 95% confidence interval, then we're looking for a Z of alpha over 2, which is our 0.05 alpha divided by 2. And when we go and look this up in a table, I see that Z of 0.025 is 1.96, which we have rounded up to 2. And this is where that empirical rule comes from that says that 95% of the data falls within 2 standard deviations of the mean, because Z of 0.025 is just about 2. So within about 2 standard deviations of the mean, we have 95% of all observations. Okay, so there is a procedure that is a useful procedure to follow when you're doing all of the problems in Chapter 8. So if we're using the Z statistic, we want to find a confidence interval for a population mean of mu. So we assume that we have a simple random sample that comes from our population data. And we either have a normally distributed population or a really large sample. And that the sigma, the standard deviation of the population, is known. If we want a confidence interval of 1 minus alpha, we use the Z table that we've been using now for a few chapters to figure out Z of alpha divided by 2. And the confidence interval on our estimate of the population mean is going to come from the sample mean, that's X bar, this Z of alpha over 2, which is the number that we look up in the Z table, the population standard deviation, and the number of samples. So let's do another example. Oh, before we do another example, just to put a little bit more stuff in here. The margin of error, your book writes this as an E, is this thing that makes our confidence interval. Okay, so here's the procedure, and I say that our confidence interval is X bar minus this number here, which is E, our margin of error, up to X bar plus E. So E, the margin of error, is Z of alpha over 2 times the population standard deviation divided by the square root of the number of estimates. And when we go and look at this, we'll have a confidence interval which extends throughout through twice the margin of error, and it goes from this lower bound up to this upper bound. So that's the procedure that we're going to follow. Oh, let me keep going with this. So now I've sort of overlaid. Actually, let's just skip that. Okay, so the example that I want to do is an example about the ages of people in the civilian labor force. So the Bureau of Labor Statistics collects information on the ages of people in the civilian labor force, and it publishes these results in the employment and earnings. 50 people in a civilian labor force are randomly selected, so our sample size is 50. That's N. And the data is displayed in the table. I'll show you the table in a minute. I want to find a 90% confidence interval for what the population mean age is, for mu, of all of the people in the civilian labor force. Assume that the population standard deviation of the ages is 12.1 years. Okay, so we have a random sample of 50 people, and we can figure out the mean of this sample, and we'd like to use this sample to estimate the mean age of the whole population. Okay, so going to our procedures, we have a simple random sample, a normal population, or a very large sample. We have a very large sample when the standard deviation is known. So for the confidence interval of 1 minus alpha, so for a confidence interval of alpha here for the 90% confidence interval will be 0.10, which means that we will be looking in our z table for z of alpha over 2, which is 0.05. So that's the number here that we'll find in our table. Okay. The first thing that is worth checking, and I want to show you how to do this on your calculator, and we'll do it in class as well, is if the data have outliers. So with 50 people, we have plenty of data to use the z-statistic analysis. But we want to make sure that there's no extreme outliers, because even with way more observations than is necessary to use this analysis, if we have any extreme outliers, then we'll have a problem. So I have gone in, and let me show you. Here's our data set. So here's our 50 ages of people, and there's our problem restated. We're looking for the 90% confidence interval. And I've actually gone in and put this whole data set in here. So it goes 22, 32, 33, 43, 60, 51, 27, and I put in my whole list, all 50 items. It took surprisingly little time. So things that we've done before with this list is we've gone zoom, we calculated the one variable statistics, and here I see that the mean value is 36.38. So I went ahead and wrote down that the mean value is 36.38. And that's really all that we need of this right now. But I want to show you how you can actually make a normal probability plot in your calculator, because that is something that we can use to check that these data are normally distributed. So if I go back up to this stat, I can see my list, and a normal probability plot will be a scatter plot that has on one axis this data, and on the other axis the z-score for the data. So let's make that. And in order to do that, I'll get out of here. I am going to use the formula for the z-score. So the z-score says that the z is x minus the mean divided by the standard deviation. That's the z-score of any number. So if I want to make the z-score of an entire list, I can call it list 2 is going to be list 1, which I have in my calculator, minus the mean value, that's this, divided by the standard deviation, that's this. So let's do that. I'll go second in L1. Let's put parentheses around it. Minus the mean value, 36.38, divided by the population standard deviation, which is 12.1. And I don't really want this to show up on my screen. What I'd like this to be is to make a new list out of this. So I'm going to use the store button on my calculator. The store button on my calculator is all the way down here. So I hit store, and a little arrow has shown up. It's going to store this in list number 2. And there we go. Now, when I go to my list, I have my original list, L1. I also have L2, which is now the z-score of all of the items in L1. So now if I want to make if I want to make a normal probability plot of this data, I go to second and stat plot. So I'm going to hit second and stat plot and go to plot 1 and turn it on. And I'm going to go ahead and select this one, which looks like a scatter plot. So we'll go there. And for my X list data, I'll keep L1. And for my Y list data, I'm going to hit second and L2. It'll make a scatter plot with list 1 on the X and list 2 on the Y. And now I can go to my graph. And nothing shows up, which is fine. If I want to go to zoom, you go to zoom and 9, and that will be the zoom stat. And that is the way that it knows to scale things by your zoom stat. So my normal probability plot looks like this. That looks like a perfectly straight line as far as I can tell. So my data don't have any outliers, and they're nice and normally distributed. So this is a great data set to be using this sort of analysis for. Okay. I think you have a homework assignment, problem on your homework with a fairly large data set that asks you to make a normal probability plot. So this is a pretty good way to do it on your calculator. It's also a way that you could do it on a test. So there we go. Let's do this problem. So example 8.5. is that I want 90% confidence intervals. Given that I know that the mean value of the sample is 36.38 years. The population standard deviation is 12.1 years. And the number of samples is 50. So now let's calculate the margin of error. So the margin of error, E, is Z of alpha over 2. Remember we said alpha is 0.1, so Z of alpha over 2 is 0.05, times the population standard deviation. Whoops, see how I wrote the wrong thing there. Mu is the population mean, not the population standard deviation. That should be a sigma, divided by square root of n. And I have managed to not bring down my Z table. I don't think I have it here. Okay, well, I don't have my my Z-score table, so now would be a great time for you to check out your own Z-score table and look for Z of 0.05. So if you look up, you will find that this could either be 2.57 or 2.58. The number is kind of halfway in between these. So I'll just pick 2.57. On your homework or on your test, I'll always accept either one. So E is 2.57 times the population standard deviation of 12.1 divided by the square root of 50. And 2.57 times 12.1 divided by the square root of 50. And that is 4.398 years. Okay, so our margin of error is just about 4.5 years. So what does that mean? If we are trying to estimate the true population mean from the sample population, I have that our best guess of what the true population mean is that it is our sample mean. Okay, so our best guess is that the average age of people in the workforce is 36.38 years. But within 90% confidence, that is that I am going all the way out here to some value, which is the critical value. And the location of this line is chosen such that 10% of the area, 5% of the area, not 10% of the area, 5% of the area is in this little wedge. The other 5% of the area is in this little wedge. So together, we have 10% of the area is not going to be included. And here is my E, my distance E, which is 4.4 years. So we're going to go from 36.38 up above by 4.4 years, and then 36.38 back down by 4.4 years. And so 36.38 plus 4.39, 4.40 years gives me 40.78 years. And down here gives me 31.38 years. Okay, so the interpretation of this is that we can be 90% confident that the population mean is between 31, well, this shouldn't be 3, this should be 9, is between 31.98 and 40.78 years. Okay, so that is another example of calculating confidence intervals given, for an example, when you know the population standard deviation. Okay. So that's that problem. And let's move on to the next one. The next question is, okay, so we had a margin of error of about 4.4 years in that last one. What if we wanted our margin of error to be a half a year? Okay, what if 4.4 years is too much? That's too much uncertainty for me to have. I need my error to be a half a year. So how many samples do I need in order to get my error to be a half a year? All right, so come back to this procedure that we used here. So our margin of error depends on z of alpha over 2. We can't change that. That we're requiring 95% confidence, so the z of alpha over 2 is set. The population standard deviation, that's also set. The number of samples is not set. As this n gets bigger, that's a number in the denominator getting bigger. I'm drawing a little up arrow here. So as this number gets bigger, this whole number here gets smaller. So there's eventually going to be a time when n is so big that it makes E be small enough that it's 1/2 of a year. So that's what the question is asking. We have to do a little bit of math to figure out how to do that. So I have that E is z of alpha over 2 times population standard deviation divided by the square root of n. Let's just go ahead and square this whole equation so that I can get n out from under the square root. So I'll square that, and I'll square that, and I'll get that E squared is Z of alpha over 2 squared times sigma squared divided by n. Now I can solve for n, and I'm going to solve for n by doing a little trick where I can switch the location of something in the numerator. This is really E squared over 1, this thing in the numerator, with the thing in the denominator. So I can do that and say that n is Z of alpha over 2 times sigma divided by E, and all of those numbers are squared. This seems like a really good equation to put on a note card. So the number of samples that I need is Z of alpha over 2 times that divided by that. This probably seems like another really good equation to put on a note card for a test. But that's the number of samples that I need. So I am left now solving for this. So n is Z of alpha over 2. For this problem, we've asked for 95% confidence. So alpha is 1 minus that, so it's 0.05, which means that Z of alpha over 2 is Z of 0.025. And, again, I don't have my table with me, but Z of 0.025, that's the number that is almost 2. It's 1.96. So we'll plug that in. So I have 1.96 times sigma, that's 12.1 years, divided by E, which is the margin of error that I want to have of a half a year. So I forgot to add it in here, but I actually have to square all of that because there's a square to the end. And when I do that, I get 22,249.8. We can't have an not whole number of samples, so we'll go ahead and round that up to the next number. So we need 2,250 samples. And that's the answer to this problem. Okay, so with 2,250 samples, we could get a margin of error what is our 95% confidence interval if we only had these 50? So it's another version of the exact same problem that we just did. So the problem that we just did, we were looking for a 90% confidence interval, and now we're looking for a 95% confidence interval. But this is the same problem. So with 50 samples, now I know that n is 50, and I'm still looking for Z of alpha over 2 to be this number right here. Let's find out what the margin of error is. And just looking at this, hopefully we will find that this margin of error is much bigger than a half a year. So hopefully we're getting something for all of these thousands of samples that we're getting here. When we sample more people, we should have a more precise error estimate. So this margin of error here should be a small number with lots of samples compared to the margin of error that we get with far fewer samples. So let's calculate what E is. It's Z of alpha over 2 times sigma over the square root of n, which is 1.96 times 12.1 years divided by the square root of 50. And calculate that. And I get 3.35. So sure enough, with a smaller sample size, we have a much less precise estimate of the true population mean than we have with our bigger sample size. So E, margin of error, is actually not what this question was asking for. It was asking not for the margin of error, but the 95% confidence interval. So that is that I need to figure out what X bar plus E is. And that is going to be X bar, I think was 38.35. Let's see if I'm right there. Oh, 36.38. So 36.38 plus 3.35. And that is 39.73. And X bar minus the margin of error, 36.38 minus 3.35. And that is 32.996. Okay, so I've been sort of rounding all of these to 2 decimal places, so we'll say that that's 39.73 with 90% confidence, with 95% confidence. The population mean mu is between 39.73. Starting with the upper end is not the traditional way to write something, so I'll start with the lower end, and I'll round that up to 33.00 years and 39.73 years. Okay. So that's another way to do the same problem. Here, this is just like what we did in the beginning. So in the beginning, we used a 90% confidence interval, and now we were asked to calculate a 95% confidence interval. And put this up here. Here is our range that we found for the 90% confidence interval. We can be 90% confident that the number is between 32 and 41 or so years. We can be 95% confident that the